Hi, I'll be talking about my modding language called Grug, and I started working on it 1.5 years ago, and it's still a work in progress, but in terms of its major features, it is pretty much done. I'll be doing this in a single take, since I don't want to listen to my own voice editing this for several hours, so apologies if some parts of the recording are a bit scuffed. This video shows off a Minecraft mod on the right, where the Grug code that runs it is seen on the left, and the code spawns a diamond item every half a second above my model block. In the video I'm also showing off that when I make changes to the code on the left, it immediately has an effect on the game on the right, which is called hot reloading. My programming language called Grug was named after a blog post called The Grug Brain Developer, and the blog post argues that a lot of care should be taken to avoid code complexity. So Grug was named after it because Grug is also trying to be as simple as possible. Grug was designed to be a modding language that is as simple as possible to use and automatically update to new versions of the game. And what sets Grug apart from more general purpose languages is that Grug knows that mods typically only aim to add basic content like more guns and creatures, and basic code like making a human spawn 3 explosions when they die. For a long time, Lua has been the standard modding language that games use, so I'm trying to supersede it with Grug. Before I started working on Grug, I worked on the open source game called Cortex Command for about 4 years, and the essence of Cortex Command is its mods, so I made it my responsibility in the team to write automated tools in Zig and Python that helped us update hundreds of mods to the latest version of the game. And this was important because the open source team was constantly updating the game, so the mods would also constantly have to be updated. My main takeaway from this experience was that mods written in Lua were incredibly hard to update automatically because of a myriad of reasons, which is where I got the idea to develop Grug. Even though Grug is a compiled language, and compiled languages like C are notorious because of their security issues, I've worked hard to make Grug as safe as possible. And in this video, I'm showcasing how Grug catches all possible runtime errors. What's especially noteworthy is that Grug functions are given a time limit, so you won't have to restart the entire game if a mod is stuck in an infinite while loop, which can happen with mods written in Lua. Grug is just a single C file that's 7,500 lines of code, and it contains an entire compiler and linker, so it does not contain something bulky like LVM or the TinyC compiler. There is also a single C header that's 100 lines of code, and it defines the API of the Grug library for game developers. And importantly, Grug's API exposes the functions Grug dump file to JSON and Grug generate file from JSON, which we'll see in the next slide. Because Grug code can be losslessly converted to and from JSON, it means that game developers are free to make a friendly UI, like Scratch's node system, instead of requiring users to write the Grug code in a text editor. So games have the freedom to generate the JSON for the Grug code in whatever way they desire. This is great for kids who don't want to download a text editor, but it's also necessary if, for example, my friends want to write Grug mods on my own Minecraft server, because I don't want to have to give them SSH access into my server's file system just to write some Grug code. Ideally, they'd just be able to write the Grug code from within the game itself in some way. You could also provide a text editor, of course, but that's a second option. You can also just write a system that allows people to drag blocks around like Scratch in order to write the Grug code. Even though Grug.c is 7,500 lines of code, I'm not a complete savage, so I split the code into 15 sections that you can easily jump between by searching for / in the file. There's a good reason that I didn't just put these 15 sections into their own files, and that's that one of the biggest hurdles for C and C++ libraries that I've seen across the years is that novice programmers often have trouble integrating those libraries into their project. And I know this because one of the most asked questions in the Box2D Discord server, which is a C library, are not about Boxed itself, but about how they should integrate Boxed's CMake setup into their own project. So by just keeping Grug a single tiny C file, people don't have to set up an entire build system just to put Grug in their simple game. One of the other major problems in Cortex Command was that just attaching an empty function to 7500 particles would bring the FPS down from 200 all the way to 50. So this is information shown in Cortex Commands using debug view. In other words, updating a single frame used to take 3 milliseconds, but by just attaching an empty function to these 7500 particles, it would now take 70 milliseconds. And this was caused by Lua bind overhead in Cortex Commands, which was incredibly slow. So I wanted to make sure that Grug did not have such overhead at all. So I read a Grug benchmark that just times how long it takes to call a Grug function 1 million times. The Grug function here increments its global integer right here by 1 every time it's called. And in this case, it also calls get1, which is a game function. And this is what actually returns 1. So basically, I'm just doing a little more than an empty function to show that I'm not cheating. So what we're doing is we're reading the global variable. I'm calling a game function, which returns 1. And then I'm setting the global variable. So at the very end, we expect this I to have the value 1 million. So this means that I can't really optimize this out in the compiler or something. This will really have to happen. It turns out that calling that function 1 million times took 3.34 seconds, which is, of course, unacceptably slow. I created the flame graphs right here using the flame graph tool from GitHub to visualize which functions were taking so much time. It turned out that my C signal handlers took up most of the time. And that's because I added those signal handlers in order to prevent the stack overflow or division by 0 from crashing the game. In order to improve the benchmark time, I replaced these signal handlers by letting my compiler output machine code that detects whether an error is about to happen. So for example, instead of catching a division by 0 with a signal handler after the error has already happened, you can prevent the division by 0 from occurring at all by checking whether the divisor is 0 before doing the division. This had the effect of making the flame graph look significantly less chaotic, as we can see here to here. And it brought the time to call the Grug function 1 million times down from 3.34 seconds all the way down to 0.23 seconds. So now it's 8 times faster than Lua bind. And this is with comparing it against an empty Lua bind function even. So I could have stopped here since this was already way faster than Lua, but I wasn't satisfied specifically with Lua bind. So what I did was I called this approach safe mode to distinguish it from the fast mode below it. And the flame graph of the fast mode looks even simpler than the safe mode, as we can see here. And that's because similar to C, fast mode doesn't inject any error prevention code. So the fast mode executed the 1 million call so fast, in fact, that it reported it as being 0.00 seconds to call it 1 million times. So I had to up the number of iterations to 1 billion just to get accurate timing measurements. And it turned out that now the fast mode was 416 times faster than the empty Lua bind function. I created these flame graphs a few months ago, but nowadays the safe mode is almost as fast as the fast mode, as we can see here, because I applied more optimizations. So users will generally be happy with the safe mode. And it should be the default that games use. You can also, of course, switch between safe mode and fast mode, and you can do so during runtime. But I'm planning to update Grug, so you can choose per individual Grug file and per mod whether you want to run it in safe or fast mode, depending on how much trust you put into whether it can crash or not. So let's talk about shared libraries. Under the hood, Grug.c transforms the Grug code into shared libraries. it can then freely load and unload those shared libraries. So here's a small demo of that. What we see here is that mod1.c defines a function called foo and it returns 7. And mod2.c also defines a function called foo, but this one returns 32. And we can now compile these to shared libraries, shared objects, and we can then open them, get the function pointer, and then call the function pointer in order to print 7 and 42. And on Windows, it's pretty much the same thing. But instead of having a C file, of course, you should imagine this being a Grug file. And instead of the main function performing the work of opening the libraries and getting the function pointers, that work is all performed by Grug.c under the hood. So the game doesn't have to worry about these implementation details. So what the game will actually do is call the function Grug regenerate modified mods, and it will compile, link, and open the shared libraries, and also check whether any of the Grug files need to be regenerated, so recompiled. The game is informed by Grug.c of which Grug files were modified and which resources were modified. And it is then the game's responsibility to update its internal data structures, like reloading the function pointers, or reloading the Minecraft textures, or reloading the Minecraft sounds. So first the game just lets Grug know, hey, I want to reload all the mods. And then Grug will tell the game, okay, these files were updated, so you have to update this gun, and you have to update this texture. So it's still the game's responsibility to decide how they want to reload the texture, because maybe they have to upload something to the GPU or whatever. Grug doesn't really care. Grug only informs the game that something happened, and the game has to handle it. So I didn't get to show off the cool features that all of the cool features that Grug has, so I want to do that. And also be going over the implementation details of how Grug works under the hood, which includes tokenization, parsing, compiling, and linking. So this is the video that we saw before, but this time we'll be walking through the code that you see on the left. This is maybe the most important slide of the entire presentation, because it gives you a taste of what programming in Grug is actually like. This is the Grug code we saw in the video. So let's look right here at the first line of code. I put the comment spawn the diamond 2 blocks above this block, above it, and the line of code right here creates a global variable called position, which has the type ID. It's important to note that what Grug calls a global variable would be called the member variable of a class in C++ or Java. So every instance of a Grug entity gets its own copy of the global variables. And the ID type itself is the, I think, defining feature of Grug that sets it apart from most other languages, because when you have an ID, it can represent any object you need. So it could be a position, or a level, or an item, but it could also be something complex, like a hash table. An ID is just a handle, so it's an opaque value that you just pass to another Grug function without really knowing what the exact value of the ID is. So it's similar to a void pointer in C or C++, except that IDs don't need to refer to memory directly. They're just a number. So more about IDs. So a well-known saying in programming is that algorithms plus data structures equals programs. And it's saying that algorithms and data structures are inherently related. So for example, if you have a sorted list, use a search algorithm that's optimal for sorted lists, like a binary search. But the reason that I crossed out data structures right here is because Grug is kind of peculiar in this regard. And that's because although Grug is a statically typed language, because you have to assign every variable type, Grug does not allow you to define new types. So, and it also doesn't have structs, enums, arrays, pointers, and so on. And that's because all of those can be emulated with the ID type I talked about. I got the idea of giving the modders IDs instead of pointers from the great blog post called Handles Are the Better Pointers by André Weisvlog. And you may know him from his so-called GitHub repository, which provides minimal cross-platform standalone C headers. So Grug itself doesn't have any data structures, but the game functions can return IDs that refer to data structures. This has the downside that if the game doesn't expose a game function to make a hash table, then your Grug code simply can't use a hash table. But for open source games like, say, Cortex Command, you can easily add a game function that allows the Grug code to have a hash table. And for closed source games like Factorio, the developers could accept requests or code contributions from the community. Or the Factorio modders could hold votes on which game functions they absolutely need to have. And another idea for closed source games like Factorio is to set up a public GitHub repository that only contains the game function implementations and that accepts pull request contributions. This probably sounds kind of ridiculous when you could instead just allow mods to define custom types like most other languages. But there are two main advantages to moving all data structures to the game engine. The first is that the game can provide super optimized versions of the data structures, even allowing game developers to do crazy stuff like using hand-rolled assembly, distributing the work across multiple threads, or even using the GPU to perform the work for large enough inputs. And this uses the fact that most game developers will be knowledgeable enough to create optimized data structures. And compare that especially to the children who are writing their very first mods and have never even heard of the term data structure before. You could argue that it isn't a big deal, of course, if children write unoptimized mods, but I've looked at the Lua code of hundreds of Cortex Command mods, and I can assure you that most mods were unoptimized messes, and that was a problem because it gave the game a bad reputation for being laggy and requiring a supercomputer to run. So by just moving all the data structures to the game functions, we allow the code of Grug mods to be both way simpler and way faster than what people tend to write with Lua. But the main reason that IDs are great is not even a performance aspect, but that IDs allow mods to be way more resilient to game updates. One of the main challenges that my mod converter for Cortex Command had was that Lua code could be so complex that it was pretty much impossible for the converter to properly update all the weirdly written Lua code that exists. But now that most of the complexity has been moved to game functions, the mod converter that I'll be writing for Minecraft, for Grug, can have conversion rules that are much simpler, since it will just mostly involve replacing game function names. And the reason that I started working on Grug was because I hated how Cortex Command's mods would become less and less playable with every update the game got. So for the sake of mod preservation and maintainability, it's essential to have IDs, because it makes Grug significantly more high level than Lua, and that makes automatically updating mods much easier. And you could of course argue that mods are never truly lost, since you could always play them in an old version of the game, but historical preservation is an active effort about keeping content as accessible as possible. So if we now go back to this code, Grug makes it the game's responsibility to decide what the ID should be. So in the case of Minecraft, what I did was I let it reserve the upper 16 bits of the 64 bits to store the entity's type. So the ID knows whether it is a block, an item, or a level. And that's useful because it allows game functions like right here, item resource location, to check at runtime that they actually got a resource location ID and not, say, a position ID. And if the player is sure that the Grug code doesn't contain any bugs, then these entity type checks could of course be skipped by the game for optimization purposes, but the rest of the Grug code probably looks complex, but that's only because Minecraft itself is a complex game. So I want to quickly go back to the video to explain why. So the first thing you need to understand about Minecraft is that blocks themselves don't run code. Instead, what you do is you create a so-called block entity or tile entity for each block that you want to run code. So in this video, the block is not running code, but there is an invisible block entity in the same position that is running the code. All right, so in the code, we start by calling the function getBlockPos of block entity, and we are passing it the reserved Grug keyword me, which is similar to the self or this keywords in other programming languages. Calling getBlockPos of block entity will return the ID of a new position, and it contains the x, y, and z coordinates of the block entity. Again, it's important to note that when a block has a block entity, that the game guarantees that it will always have the same coordinates. So we now have the position of the block, and we can directly pass it to the function getBlockPos above n, along with the argument 2. And this function will return another ID of a new position object, which contains the x, y, z positions of the block raised up by 2 blocks. And that's where we want to spawn the diamond eventually. So we now have a position variable right here that contains the position in the area where we want to spawn the diamonds, and then the rest of the code is pretty much the same thing over and over. So once you understand this first line of code, understanding the rest of the program becomes much simpler. So let's quickly move on to the second line of code. The comment above it states the dimension, so overworld, nether, or end. And in case you don't play Minecraft, these are the 3 dimensions in which you can play the game. So the line level ID equals getBlock entity level me is getting the level which we are in and saving it in a global variable called level. On the right side, we see most types that Grug has. So we've already seen the ID type right here. But on the third line of code, we'll get a new type called string. And the floating point 32 type right here is used to store the x, y, and z positions separately. And there's also an i32, which is an int. So it will just count from 0, 1, 2, 3 in this case. It's used in order to track how often this function right here has been called. So finally, we have the bool type. And if you look at the code, you won't actually find a bool variable. But what we do have is an implicit bool, because what we're doing here is we're doing a comparison, and this will either return true or false, which is a boolean. So now you know most of Grug's types, ID, string, f32, i32, and bool. So let's speed through reading the entire program now that you know how to read the code. So we get the full name. So the name diamond is actually called Minecraft diamond. Then we create a diamond item. Then we get the coordinates of where the diamond is spawned. We create a diamond item stack. And we track how often onTick has been called, and we'll see why that's important. So now the last thing to know is that the onTick function itself is called by the game 20 times per second. And that's because the game runs on a 20 ticks per second clock. So if we want to spawn a diamond twice per second, every half a second, we need to use a global tick variable, which we do, and we let it count up to 10. And then once it reaches 10, then we reset it back to 0. So we increment the global variable by 1 and return from the function until 10 ticks have elapsed. And once they have elapsed, then we actually spawn the diamonds. This is a really basic way to create a timer, though, of course, if the block only wanted to spawn an item every hour instead of every half a second, it would, of course, be way more efficient if the game just gave the mod a game function in order to set a timer, so it doesn't have to be called 20 times per second. But that's something the game could add. All right, so what we now have left is we create the diamond item entity using the level, the x, y, z, and the item stack, which were the global variables that we defined here. Then we just remove the random velocity that spawned items are given, and then finally we spawn the diamonds. Okay, so this code shows off an onTick event handling function. The blocks also have an onBlockBroken function that the game will call for us when the block is broken. So you could add that to this Grug file too. It's important to note that most of the functions that we're calling here are just wrappers for the Minecraft Forge or Fabric or other Minecraft APIs. So you would use nearly identical Grug code for other projects. For example, for Factorio or Blender, or if you want to use CUDA or HIP for GPU programming, you'll always just have game functions and IDs, and those are the main two ways you interact with the program. So another thing is that Grug currently has an i32 and f32 type, but I don't really want to add another type for 64-bit integers and 64-bit floats. And it's also kind of hard to explain to children what the difference is between an i32 and an f32. So instead, I'm considering replacing those types with a new number type. And that's inspired by Lua, which also only has a single number type. Even though it's not explicitly stated in the code, every number is just a 64-bit floating point number under the hood. So in C, that would be a double. And the important point is that when you use a double to represent an integer, there is no rounding error at all. So going 0, 1, 2, 3, 4 is completely safe. You can just use a number as if it were an i32, and that's completely safe. So I could do that. In order to prevent weird bugs in games, like for example this screenshot of Balatro, I think I'll also let Grug detect and throw a runtime error if the values infinity and not a number are encountered in safe mode. So this is a famous example seen in Balatro where if you reach a high enough score, it displays non-exponent inf. And this could be considered a feature, but in my case, I think it would make modding simpler if you didn't have to worry about weird values like nan and infinity. On functions like onDef can't return a value, but what they can have is an argument like the n integer right here. So what I'm showing off here is how you implement the famous Fibonacci function, which returns 55 when n is equal to 10. And the Fibonacci function has a recursive definition. So I have written the recursive Grug function, helperFib, to calculate its value. And first we have the base case of the recursive function right here, which are n equals 0 and n equals 1. And if n is 2 or greater, then we don't return immediately, but then we go here. We recursively call ourselves with n minus 1, and here with n minus 2. And what should be noted here is that if you pass an n value that is very large, like for example 1000, then any stack overflows caused by the deep recursion are caught by Grug in safe mode. So if the say onDef function takes too long to finish of zombie, then it also automatically times out that function as we talked about before. And these two facts combined make recursion completely safe to use whenever you want in your Grug code. So stack overflows and timing out are completely safe in Grug. One of the main choices I made in order to make them more maintainable is to require every variable to be explicitly assigned a type, as we saw previously. The code on the left is the approach Grug takes of requiring every variable and parameter to be explicitly given a type, while the code on the right is the approach a few people have suggested to me of having variables and parameters be implicitly typed based on their usage. So both the left and the right side, in this case with this code right here, will throw a compilation error because they are mixing types. So what we're doing here is we're passing 42 to helper foo, which expects a number, which is correct, but then we're calling helper bar with that number, but helper bar expects a bool. So we get the error helper bar expects n to be a bool, but got number in helper foo. While on the right, because of the implicit typing, we get a much more verbose error message. So Yeah, with this inferred types, you may have to dive into a way deeper rabbit hole that's many function calls deep, and that's why I decided to keep every variable explicitly typed. So talking about tokenization in Grug. So the first step of the Grug compiler is to read the text of a Grug file right here. We then need to turn those into tokens. And in the function on the left, there are words, parentheses, colons, braces. So we create an enum called token type for them. Let's also create a struct called token, which holds a token type enum and a string pointing to its text. If we then parse that function, we get this array of tokens. And the first token is the word on a, because it's the first thing in the Grug file here. And the second token is the open parentheses after that, which is here in the text. In this case, I stored a null pointer, but I could have also just stored the open parentheses. This is the same array of tokens that we saw in the previous slide. So using recursive descent parser, I turned the tokens into statement structs, on functions, and expressions. And I did that in order to form a syntax tree out of the tokens. What we see at the top of the tree is the onA function, and it takes a parameter called n, which is a 32-bit integer, and the function prints n, and that function can be decomposed into the name of the function, which is print i32, and the name of the argument, which is n. So if you're interested in the details of the recursive descent parser, you should look up Crafting Interpreters by Robert Nystrom, which is an awesome book that you can read for free online. And because it's free, you can look up chapter 6.2 for his recursive descent parser explanation if that's all you're interested in. I also recommend the blog post series Writing a C compiler, and because the series walks you through writing a C compiler that emits assembly files. And every single blog post entry is atomic, so you don't have to read every single blog post. You can just start with the first one and work your way through to part 10. It was also turned into a book, which you can also read instead of reading the blog post. So now that we have a syntax tree, let's quickly go over what compilation means. Ignore the highlighting here, there was a mistake. So we have a function that returns 42 plus 1, which is of course 43. And we can see how this C code right here would typically be optimized to just directly returning the number 43 in hex. And we can see that there is no add instruction going on, even though there was an addition here, because the compiler was smart enough. And this is what it looks like in assembly. What it does is it just moves the number 43 into the register called EAX, and then returns from the function. This assembly is just a textual representation of the bytes, which look like this. You can see how the ret instruction right here is just a C3 hexadecimal byte in the executable itself. So let's now try writing this same function in assembly ourselves instead of using C. And let's do that using NASM with Intel syntax. So writing the assembly ourselves gives us full control over the generated machine code. So what we see is that we see the add instruction in this case, and it has not been optimized away. I needed this full control over the generated assembly because it allowed me to write hundreds of tests for the Grug compiler by verifying that the Grug compiler's output is identical to the NASM assembler. So basically, I didn't want to make my Grug compiler an optimizer like this. I just wanted to keep it as bare bones as possible. So I could use NASM in order to basically verify that my compiler's output was correct. Here we see one of the tests. Grug has 377 of them by now. On the left, we have Grug code, which calls the game function initialize with the argument 1.1 plus 2. And we just want to test whether this indeed passes the number 3 to initialize. So we're just testing addition here. On the right, we have C code, and that C code asserts that the test called initialize exactly once. So first it was 0, and then it was once called. And we also assert that the result of the addition was 3. So if this test passes, then we know that addition at least somewhat works in Grug. I also use gcover and libfuzzer to make sure that I have tested all lines of code in Grug.c, and to make sure that there is no way to crash Grug.c with weird inputs. So although we have asserted that the result is correct on my computer right here, it is possible that this Grug code will crash on someone else's computer, or that it will output 4 instead of 3. And that's because although Grug produced a shared library for the Grug code that seems to work fine on my computer, it is incredibly hard to make a compiler that follows the shared library format that Linux specifies 100% accurately. So it is, for example, very possible that this Grug code right here produces a different result, so fails this test on a different CPU. And that's because a lot of things can go wrong when you write a compiler from scratch, like I do. So that's why I needed this NASM assembly in order to basically check that this code right here generates the same assembly as my handwritten NASM test. And that's what we see right here. So this is what I call ground truth for what a correct shared library should look like for this test. I can't use the assembly output of C for this job because, as I said, C compilers output assembly that is way too overcomplicated and over-optimized for Grug to mimic. So instead I use NASM because it's one of the most popular assemblers. And you should just imagine that this code on the left would be placed above the top here. So this is just a single NASM file. So what we see on the left here is that we define global variables in the data section. And then the first global variable in it is global size, which tracks how many bytes the game must allocate for the global variables of the file. In this case, it's 8. We then go to the text section, where we include 2 other NASM files I wrote, and this is like a include statement in C. So this is just copy-pasting the contents of defines.s and macros.s. We then declare which game functions and Grug globals our test will use. And then on the right, we see that we have on a game function. It would take too much time to go over every single line of assembly, but we don't have to look at all of it to get an idea of what's going on. So instead of every function, there's some boilerplate right here that we can just skip. We then get to the first interesting part, because this is an if statement that checks whether the global variable called Grug on functions in safe mode is true or false. In case it is true, then what we do is we go to the safe implementation right here. In case it's false, then what we do is we go to the fast implementation below. And the fast implementation is, of course, way simpler than this one. It just adds 2 or 1 plus 2, which equals 3, and then it calls game function initialize, and then it returns. So now we can move on to the next one, which is about how linking works in Grug. Because we now have the machine code for the function, but we still need to turn it into a shared library at some point. Because Grug currently only targets Linux, my compiler had to output shared libraries that follow the so-called executable and linkable format. And there's this beautiful diagram right here, which you can find on the ELF format Wikipedia page. And it helped me a ton for understanding the structure of ELF files. If we zoom into the diagram, we learn that every ELF file must start with the bytes hex 7f and then ELF. So the first thing that my compiler does when it generates a shared library is push these bytes into the shared library like so. I've easily spent over 100 hours using readelf, xxd, and oba dump while reverse engineering the ELF files that other compilers would output, like C or NASM, and also while fixing bugs in my own compiler. So if you write your own compiler, I can highly recommend these tools. Okay, back to Cortex Command for a second, because one of the biggest problems that Cortex Command had is that the solo developer of the game, back in the day, never published any documentation on the game's modding API. So because there was no documentation, people would join the Cortex Command forum to ask for help and to share snippets of code with each other, which is what we see right here. If the game's modding API had proper documentation back in the day, I'm pretty certain that the game's modding scene would have flourished even more, since modding would have become much more accessible. So one of Grug's goals is to solve this problem of not having any documentation. And an arguably even bigger problem that Cortex Command had was that mods were not secure, because they could for a really long time secretly read all of your files on your computer. And this Lua problem isn't limited to Cortex Command, as we can see from this Stack Overflow question. And I also remember seeing a YouTube video, which was clickbait, that claimed that Lua was insecure, which also showed off that in a different game, mods could secretly read a bunch of files on your computer. And of course, Lua itself isn't secure, but the game but the game using Lua is, because the game forgot to disable Lua's standard library called IO that allows mods to read and write random files on your computer. So another one of Grug's goals, especially because it's a compiled language, is for it to always be completely secure, and the game developer shouldn't have to turn off any standard libraries. So now we get to Grug's unique solution to these problems, and that's that it's the game developer's responsibility to create a file called modapi.json. And this file is read by the Grug compiler, and it also guarantees that every game using Grug will have modding documentation, security, and type checking in one. So I've got an example modapi.json file right here, so let's walk through it. So the JSON file only defines two things: entities and game functions. This game only defines, for example, a gun, which means that mods are only able to create new types of guns. The three Grug files we see right here have -gun in their name, because that's how they inform the Grug compiler what kind of entities they are. So the JSON file also states what it is, so the gun that the player fires by holding the left mouse button. And then we get to its on functions. So it, for example, has on spawn right here, and below it also an on fire, which the game will call whenever the gun is spawned into the world and whenever the gun fires around, respectively. The game also exposes two game functions to mods, which are the only game functions they are able to call. So they're not able to open random files on your computer because Grug only allows the mods to call these. They are set gun rounds per minute and print string. So if we look at set gun rounds per minute, we see that it also has a description and it also has arguments. So in this case, it expects a round per minute, which is an i32, so an integer. Then we have print string, which prints a string and takes a message. So in other words, Grug doesn't have a standard library, unlike C and Lua, and that's because the game developer is expected to provide the standard library themselves. And this is nice for modders, actually, because they won't have to wonder whether a function is a built-in function defined by the language or defined by the game, like, for example, Lua's print and toString functions. This modapi.json can also be safely shared with gamers, because this doesn't expose any of the internal source code of the game. And that's something that closed source games can find very important. Gamers can then use this JSON file as well to generate simple documentation websites using just a little bit of JavaScript or Python. And that's amazing for the game developer because it means they don't have to spend any time on making the documentation look pretty on a website. They can just let the players figure it out using the JSON data. All right, that's it. So remember this code I showed a few slides back? It it shows how games would use Grug's API in practice. And in the next slide, I have a video that shows off what this reload modified entities function does. So using that main function that I showed, Grug makes it really easy to reload the gun's texture in real time when the texture is modified by, say, an image editor, like in this video. What happens here is that Grug checks every single frame, though that can be, of course, configured, whether the PNG of the gun was modified. So what we see here is that the gun looks like this at the start, but then we use Pinta in order to paint on it, and now it suddenly has a little bit of pink on it, and the game will instantly recognize that. And it also shows off how you can change the name from m60.png to another texture, and then that will also immediately be reflected in-game. So Grug constantly checks whether the PNG was modified, but you may be wondering how Grug knows that it should check that file, right? So let's say the mod API exposes a game function called setGunSpritePath. If a mod calls this function and passes the string m60.png to it, the code compiles and runs just fine. But if we then try calling that game function while passing it the string m60.mp3, Grug will throw a compilation error, and that's on purpose. And that's because, in this case, the mod API right here defines that the string should be a special type of string called a resource. So it will only accept PNGs, is also what it specifies. So that is why right here, the MP3 will throw an error. The resource type also means that when the m60.png file is moved to a different directory, the Grug compiler will immediately detect that and report the problem to the game. So you don't have to worry about moving files around and breaking your game silently. You can just work on the mod while the game is running. Another important thing to note is that mods can only access resources inside of their own mod, so only stuff that they ship. And that's a deliberate choice, because what would happen with Cortex commands was that mods would often break silently, and that's because they depend on external files that did not exist anymore or had been moved to different spots. So you can imagine that this mod might have used a PNG from a different mod, but what if that mod got changed? Then suddenly this will break. So this ensures that if something like that happens, that you're immediately informed of the issue. But by just only having the resource in your own mods, you don't have this issue at all. You always can only access your own resources. So I want to discuss a big limitation that Grug had a few months ago and how I resolved the issue. So this is a screenshot of a dropship from Cortex commands, and the players of the game see this as a single giant lump of metal, but in reality it is composed of several smaller pieces. So you have the main body of the dropship, you have the left and right thrusters, you have the left and right doors that can open up, and finally you have the left and right turrets that automatically fire at enemies. Cortex command attaches all of these entities together based on its own weird mod configuration file format, and the thrusters could then be controlled using Lua code. But Grug mods aren't split between configuration and Lua files, because Grug files are self-contained. So another thing is they can't call functions from other Grug files. They can only just call game functions. So it wasn't really clear how you would make this dropship using Grug, because you can't really split this dropship into several Grug files if Grug files can't communicate with each other, right? But I'll show you the solution that I came up with. So let's say we have a mod API that exposes the game function setLeftThruster, which accepts the name of a thruster right here. This setLeftThruster function accepts an entity as its argument, which is a new type Grug type that we haven't seen before. And it states that it should also specifically be a thruster entity. So what I've done here is I've written some code in my mod called Sander, and it's jet-thruster.grug. So what I can then do in a different file is I can then use that jet by just calling setLeftThruster. So this is a game function, setLeftThruster, and it expects the name of a thruster that you added. So in this case, I called it jet, as we saw here. So if I then create a subdirectory in my mod called foo, and I were to move the jet-thruster.grug file into it, the setLeftThruster call that we do right here will still be able to find the jet, even though the file was moved. And if I add a new mod called Bob, let's say, which has an ion thruster in it, then my Sander mod can still use the ion thruster by specifying the mod name in front of it. So this is like a namespace. This is saying which mod it should come from. But if I were to, however, create a file called ferrari.car.grug, this will mean that when you then call setLeftThruster Ferrari, that this will cause a compilation error. And the reason that this compilation error is thrown deliberately is because if we look at the Ferrari, it's a car, it's not a thruster. And we specifically specified that the setLeftThruster expects a thruster. So that's the reason that this will throw a compilation error. And that makes sense, because how does it make sense to put a Ferrari as a thruster? You expect some sort of engine, like an ion engine or a jet engine. And this is great, because what this means is that the game can just ask the Grug compiler which mods you depend on. And this makes mods super compatible with one another. So instead of just having to guess which mods you need, this information right here specifying I need the mod called Bob is enough to gather all the dependencies that you have. And Grug also checks every single frame that the dependent on entities still exist. So you can freely edit your mod while the game is running, and Grug will automatically throw a compilation error if you forgot to add an entity. Okay, so I also wrote a bunch of Minecraft tests because I'm now working on a Minecraft mod with Grug. It has about 98% coverage of its game functions, which there are 64 of. And I wrote 175 tests for those game functions. So on average, about 3 tests per game function. And we see some of them right here. So for example, there's a function called block, a function called block boss, box i32, destroy drop block, and so on. And what's cool about these 64 game functions and these tests is that they are physically simulated in Minecraft. So in this screenshot, what we see is a bunch of green beacons and a single red beacon. And that single red beacon represents that one test failed out of all the tests. So talking about coverage again, the green lines right here represent the lines of code that our tests cover, and the red lines represent the lines of code that our tests didn't cover. So at the bottom, you see the test that I wrote in order to cover those red lines right here. So what we do is we call place block, but in this case, we pass it an ID of the wrong type. So it will now throw an error saying expected block state, but got box i32. And this will cause the red lines here to turn green, and for my coverage information right here to go up. All right, so if your Minecraft mod needs to use a complex data structure, like for example a hash set, then you can actually get one by just calling a hash set function in my Minecraft mod. So in this example, I'm using the set to store the ages of all people right here. We can add values to it by calling hash set add, where we pass it the ages set. that we created, and we also pass it the value that we want to add to the set. In this case, the box i32 function takes a number, so 7 in this case, and wraps it in an object. So this basically allows you to just have a hash set add function that takes one ID, which is the set, and another ID, which is the value to insert into it. In C++, you'd use templates to make a hash set that accepts any type, but since Grug doesn't have templates, we just have to wrap the value. And Java calls this boxing, which is why it's called box, of course. And what we then do on the right is we can create an iterator over these ages, and we then call the iterating function, which returns a boolean, signifying whether we have iterated all the values in the set. If we have more values to iterate, then we enter the while loop, and we call the iteration function to access the next value, which is an ID. So in this case, the value is, of course, a box i32, so we have to pass it to unbox i32 in order to print 7 and 42. Something I've written about on my blog post is that Grug isn't a garbage collected language like Java or Lua, and this is possible due to a single very specific restriction that the Grug compiler enforces, and that's because if you create a global ID called opponent right here, and you have an onFoo function that attempts to change the ID of the global variable, then Grug will throw a compilation error. So this means that there is a very clear distinction between local variables and global variables, and this makes managing lifetimes and garbage collection way simpler than in Lua or Java. It means that there's not actually any garbage collection. It just automatically gets freed at the end of the onFoo call. You can read more details if you're interested. And in order to prove that Grug mods are easy to convert between different game versions, my goal is for Grug to work across all Minecraft versions and all mod packs. And right now I only got Minecraft 1.26 working, but I've started working on other versions. And this is the end. So this presentation was based on my blog post, which you can find right here for some more juicy details. And in the future, I'm planning to, for example, write a own operating system called Grug OS, but that's probably far-fetched. But I do really want to add debug symbols in order to make sure that if you attach a debugger to the game, that you can actually step through the code and see all the intermediate values. And this was it. So if you're interested, check the description for more details, and thanks for listening.